crap. Welcome to the first part of Chapter 4, Test Hints. This is the full Chapter 4 test, but the first half of it. Some of the people sitting here in the studio audience today are also looking at their midterm exam test hints, because they'll match. The first test hint says how to find or calculate the speed of a wave. So you need to know some basic equations. One of those is that C equals frequency times wavelength. Okay? Frequency times wavelength. C is the speed of light. F, or nu, stands for frequency. And lambda is our symbol for wavelength. Are we good with the symbols? We know what they mean? Okay. So this is a general question that asks you about these variables. It'll be pretty straightforward. Number 2, what variable is constant for all types of electromagnetic radiation? Well, that would be the speed of light. Speed of light is a constant. This is speed of light in a vacuum. 3.00 times 10 to the 8th meters per second. Okay? So, wavelength may go up, which means frequency goes down, but the speed of said wave will be a constant at 3 times 10 to the 8th. Or we may have a short wavelength and a high frequency, but the product of those is going to be a constant. Number 3, how wavelength and frequency are related. I think I just covered that. They are inversely proportional. So when one goes up, the other goes down. We have very long waves at the red end of the spectrum. And then as we get to orange, it's kind of long but shorter. Yellow I don't have a marker for. We get to green, and it's shorter. It's a horrible drawing. We get to blue, and it's very short. And we get to purple, and it's really, really short. Okay. Number 4. When or under what conditions electromagnetic radiation behaves like a particle? This is a key concept from the chapter, and I do believe this one shows up on your midterm exam hints as well, right? Electromagnetic radiation travels through space as a wave. Okay? EM radiation travels through space as a wave, but when it hits matter, it acts like a particle. And we know that because only certain amounts of energy are absorbed by the atom, or by the electrons in an atom, when they go through those quantum jumps. Our evidence is the reverse of that. When the electrons spit out that energy, we're seeing certain colors, certain frequencies, certain wavelengths, only specific amounts. So we know that that wave, the light, is coming off as in these little bundles. So that's that whole wave-particle duality idea.
When it hits what?
Matter. When it hits atoms. When it hits atoms, it behaves like a particle. Number 5, how the photoelectric effect works, how does it affect metals, and why electrons are ejected. So, again, the idea that the electrons in an atom have to absorb the right amount of energy to be able to move an energy level. Okay? And you saw that little animation in the notes on your online textbook. You have the animation of the photoelectric effect. I had the demonstration with the lasers on the phosphorescent paper, and the red laser and the green laser didn't affect the paper, but the blue laser left that glowing stream, that glowing streak, because those electrons were excited. So when they first tested the photoelectric effect, they got current to flow from the bulb. When they shined the right colored light on it, the right frequency, right energy, electrons would flow. They actually measured an electric current. Okay? If the energy isn't enough to excite the electrons in that metal, then there's not going to be any current. If it is enough, then there will. Why are you all so quiet today? Very quiet.
Yeah, I don't understand that.
Don't understand what part of it?
Most of it.
Metals.
Huh? Metals are what they were shooting it at. If the metals can eject electrons, if you excite the electrons enough, they'll eject them, and that's the current that flows. A current is just a stream of electrons.
And that's just a photoelectric effect that we think.
Right. Okay. Number 6, how to compare the frequency and wavelength of two different waves, for instance, red and blue. So, we have that red wave there, and we have a blue wave here. What is the frequency of the blue wave compared to the red?
Higher.
Higher. Higher frequency. And how about the wavelength?
Lower.
Low. So I'll ask you about light of two different colors, because that's the easiest. Or we could say maybe ultraviolet compared to radio waves. You should know the differences on that whole spectrum, from radio, TV, microwave, infrared to visible light, to ultraviolet, X-rays, and gamma. You should understand where everything is on that spectrum. The lab you just got handed back, the bottom of it, there's that little chart that shows a wave kind of like this and lists the whole thing. You might want to write that on your hymn sheet for your exam. Okay? So this is going to see, frequency A compared to frequency B, or EM radiation A compared to EM radiation B, which one has the higher frequency, or which one has the longer wavelength. And they'll have some other information about that to help clarify. Number 7, the two official names for little packets of EM radiation. Two important words. Photons or quanta. Quantum is the singular. Okay, and those names will be used interchangeably. Little packets of energy as absorbed by electrons in an atom.